All right, so we'll go ahead and get started again. Our next speaker is Tim Martin, who works at Cisco. He's been at Cisco for, well, longer than any of us really want to admit to, but something like 20 years. And been doing this networking gig for even longer than that. So Tim's a great presenter, and we're really excited to have him here today to talk about some IP multicast stuff, which, multicast is such a big part of IPv6 on the stack management side of things that it's an important topic that we haven't covered in past summits. So we're really excited to hear Tim talk about this today. Let's see. In Tim's current role, he's a solutions architect based on the U.S. public sector space. Tim has the distinction of Multi-Protocol CCIE 2020 in June of 1996, and he's participated in a number of different industry events and has a gold certified engineer from the IPv6 forum. So please welcome Tim.
Thanks, Dan. Thanks all. It's a pleasure to be here and to speak to you about IPv6 Multicast. Dan mentioned the IE number, and 2020. I thought, okay, that's a great accomplishment. But there was a fellow who spoke a little earlier today, who somehow managed to be ahead of me. He always is. Mr. Doyle's number is actually 1919. Right. So I like to think that I follow him in order, and it'd be nice to follow him anywhere. Right. What a wonderful talk this morning. So contact information. Please follow me on Twitter. I only use it for IPv6. I promise you will never know what I ate for lunch. I just use it to update really relevant stuff to the IPv6 cause. So contact info here. Of course, this material that I'm sharing with you will be available today. Let's get started. Why multicast? Well, multicast actually arrives in a lot of technologies that we're using in our enterprise networks, that we may be using in our service provider networks, and certainly it'll appear in the consumer market. We'll see multicast technology in car-to-car communications. We have yet to invent all of what we're going to use multicast for. Everybody's familiar with the millennial generation, ages 18 to 34? And there's some in the room. They will be the bulk of the U.S. workforce by this time next year. Right behind them is Generation Z. There's an app for that group, right? We old guys like me have yet to fathom what we're going to be able to do with multicast. I'm not going to spend a lot of time talking about service-oriented multicast and application-level multicast. I'm going to spend a lot more time talking to you about what's going on with multicast in your networks today and what we need to do to ensure that IPv6 has a smooth transition into your networks. So here's the IPv6 address family. And it's a lot like Thanksgiving dinner, right? You got the adult table, you got the kids table, and then you got that drunk Uncle Salty, who last year snuck a fifth of bourbon in his boot and made a complete friend of himself. You see, when we look at the family, there's certain members who are going to get to sit at the adult table, and then there's others who sit at the kids' table. So I would submit to you that what's sitting at the adult table, really paramount to your understanding, from the multicast family is Solicited Node. From the unicast family is link, local, and global. These three members of the family sit at the adult table. Everybody else sits over at the kid table. They have a role, but they're kind of bit players. Now, remember Uncle Salty? We didn't even invite him to the party. He's what's known as broadcast, and he doesn't exist. He doesn't even get to show up for Thanksgiving. And the implication is that we're going to use a lot of multicast to do what broadcast did for us in the legacy protocol. We start right away at layer 2. As a technologist in the networking world, I love to work my way up the stack. And so right away we see that IPv6 was given a new ether type, a different ether type from the legacy protocol. But what's really important at layer 2 relative to multicast is this. This is the IPv6 layer 2 multicast address. It begins 3333. Now, how do I know that's a multicast? Is it just because Tim's standing before you and said so? Or is there a really cool trick that's going to wow and impress your friends at Beer and Gear tonight? And of course, there's a really cool trick to Ethernet. You see, if the least significant bit of the first byte of any Ethernet header is set to a 1, it is said to be a multicast forever and ever and ever, with only one exception. And that's if all bits are set to a 1. And we know that as a broadcast, yes. Now, the second least significant bit has bearing as well. If that bit is set, it indicates to us whether this Ethernet address was locally administered, or if it's a 0, whether it was assigned to a vendor as an OUI. So let's look at how we map addresses. You see, for every layer 3 multicast address in IPv6, we must map it to the corresponding layer 2 multicast format. And as you can see, the last 32 bits of our layer 3 maps to the last 32 bits at layer 2. Now, another little interesting piece of trivia. Why 3333? Anybody? Anybody ever hear of Steve Deering? You know, kind of had a little something to do with multicast, right? He was working at 3333 Coyote Hill, Menlo Park, at the time he applied for this MAC address space. So there, trivia. More, I'm telling you, the friends tonight are going to be just impressed, aren't they? You probably better not leave the Beer and Gear with this kind of information, though. Somebody might want to have you locked up. So here's another example of mapping a well-known multicast address to the layer 2 corresponding multicast address. So the rule, every layer 3 multicast address in IPv6 must map to the corresponding layer 2 multicast address. This is the format we use to do that. Now, what about those layer 3 multicast addresses? First specified in RFC 4291. You should all be aware that anytime I see FF beginning a V6 address, that it's a multicast. So the first 8 bits are well defined. They're all set to 1. The next 4 bits are flags that we use to help us understand the variable component of this multicast address. You'll see those last 112 bits are the variable component that we're talking about. So the flags, the first flag is set to 0 and is reserved for future use. The next flag is the R flag, and it identifies for us whether or not we're carrying rendezvous point information in this multicast address. For those of you who have done multicast with the legacy protocol, you've probably gone somewhere in your network and configured a loopback interface to be a rendezvous point. And then you go down and configure all your layer 3, your routed infrastructure. You point them to where the rendezvous point is located. And this was typically a manual configuration. It certainly was a manual configuration when these RFCs first came out. Now we've had some things like BSR and Anycast RP show up and make it a little more automated, but the designers of the V6 protocol didn't have that luxury when they came up with this scheme, which is a wonderful scheme because I can literally carry the rendezvous point location, its IP address, in my multicast address. So I don't have to go configure all the equipment to know where the rendezvous point is. Next, we have a P bit, which is used to tell us that prefix information is contained in the variable component of the multicast address. Well, if I'm going to have a rendezvous point with a legitimate address, I'm probably going to set that P flag as well to say, hey, there is a 64-bit prefix. The next bit we see in the flag component is the T bit, or temporary bit. If I was, and I am streaming right now, hello out there in Streamland. If I was streaming a radio session over multicast, I would be setting the T bit because it's a temporary multicast. Whereas if it's cleared in 0, then we know it to be a well-known multicast address, and we use a lot of well-knowns in protocol maintenance. The next 4 bits define the scope. Essentially, the scope is how far this particular multicast stream can radiate. Most of the multicasts we deal with will be link scoped, 2. Some will be site scoped, 5. And if it was me doing Tim's IPv6 radio, I'd go global scope, echo. We have a relatively new scope, 3, realm. Not that 3 is new, but the definition of using realm scope is new. It's set aside for automatic configuration beneath the site boundary. And so where might we see that pop up? We kind of had a talk on it a little bit earlier, right? Probably going to see it being used in IoT type devices. Here's an example or a chart of some well-known multicasts, and you can see that we use these for protocol communication, for control plane, if you will. Take a look at the OSPF routers and OSPF designated routers, FOX 0, 2, 5, and 6, respectively. It aligns very well with your legacy protocol knowledge, right? 224.0.0.5 and .6, right? Those are the multicast addresses that the legacy protocol uses to peer and exchange routing information. So good news is we preserved that last digit to kind of help us smooth the transition a little. So let's look a little deeper at what happens when we construct one of these 128-bit multicast addresses. We already talked about the first 8 bits being set to a 1 to indicate that it's multicast. Then we've got our flags and our scope. And I will explain a little deeper this flag section in about 2 slides, because it's technically, for this particular RFC, those bits are all set to 0. That whole 8-bit field is actually reserved and set to 0. I always called this the missing bits when learning IPv6 multicast, right? Because there was these 8 bits that were just sitting there, did nothing but zeros. Next, we have 8 bits that define the prefix length. Did we need 8 bits to define a prefix length? No, but that's what got set aside and reserved. Okay, and then we follow that with the 64-bit unicast prefix, and then 32 bits of unique material that we actually take from the unicast address assigned to the specific host that would be using this multicast address. So in a nutshell, we're going to map the last 32 bits of our unicast address to the last 32 bits of the multicast to form the specific multicast group ID or channel that we would join. Then we have RFC 3956, and this is the RFC that talks about how we encode the rendezvous point information in the multicast stream address. You'll notice that there is a field in red there called the RPID, rendezvous point ID. It's a 4-bit field. So the implication is that for a given stream that is a 64-bit reference from a single host, my rendezvous point only has 16 values available to me. But if you're building a network with more than 16 rendezvous points, believe me, you're going to have much bigger problems than needing a 17th. So the way it works is we set that OR flag, and it tells software, hey, there's prefix information in the group ID. Grab that prefix information, then reach into that RPID field and concatenate whatever value is there onto the prefix. You as network administrators would have gone and configured that rendezvous point as a loopback somewhere in your infrastructure. And so now I can carry that information in this stream address without having to go and configure all the devices in the network to point it to the rendezvous point. We have a recent RFC, 7371, and this is why some of my slides are a little off. What 7371 says is we probably are going to run out of flag bits, right? We already have the reserved that we didn't specify a use for. Then we have the RPT flags. So 7371 says we're going to go over to these 8 bits that were reserved in the past, save for 3956 where we used 4 for the RP ID. But now we're going to create a second flag field. Now, I am not aware of any specific flags that have been deployed in this second flag field to date. But the point is that we are expecting to use this field in the future for yet to be developed flags. Now, I think it's pretty heady that the IETF would be ahead of that game and say, you know what, we're probably going to have these applications in the future. We better have some space to do some delineation or identification of multicast addresses as more and more applications are developed and more IoT types of things appear. Solicited node. This is probably the least understood multicast address and the one that needs to be understood the most. We use the solicited node multicast address to do address resolution. It is our ARP replacement. In a nutshell, every unicast address in IPv6 is required to construct a corresponding solicited node multicast address. And I'll get into the details of how that happens in just a moment. But in a nutshell, starting off with duplicate address detection, we're going to use our own constructed solicited node multicast address to verify uniqueness of that address on a given layer 2 segment. So the way we do that is we use an ICMP v6 neighbor solicitation with an unspecified source. Now, for those who don't know, the unspecified source is simply 128 zeros. Well, think about it. We want to verify the uniqueness of an address for use on a domain. We certainly wouldn't want to source a packet with that address before we verified its uniqueness, right? So we use all zeros as the source. The destination is a solicited node multicast address that corresponds to the unicast address we're trying to verify for uniqueness. If that address was in use, the owner of that address would respond with a neighbor advertisement. You'll notice that in this particular case, this should be the only neighbor advertisement you ever see where the S flag is set to a 0, but the O flag is set to a 1 in the flags field of the neighbor advertisement. Now, the S means a response to a solicitation, and the O means override information. And basically, when this guy responds, he's telling the initiator, hey, I own this MAC address and it's tied to this IP address, or vice versa. So let's look at solicited node multicast format in a little more detail. The first 104 bits are well defined. You see that up there, FF02::1:FF. So those 104 bits are defined. Each and every unicast or anycast address in IPv6 is required to construct this solicited node multicast format. So it's pretty straightforward. Here's a unicast address, a link local unicast address. I'm going to throw away the first 104 bits and append them to the solicited node multicast format. So the last 24 bits map onto that format. Now, I have a layer 3 multicast address. What was the rule for that? I have to construct the corresponding layer 2 multicast address. So I'm going to grab the last 32 bits of my multicast address and map them to the layer 2 multicast format. Make sense? Sorry to be so geeky after lunch. It keeps you awake. This is what it looks like in the wild. So you'll see that I went in on this interface and I configured a link local v6 address. When I did configure that link local address, the last 24 bits were appended to the solicited node multicast format, and I joined that group. It's like I'm listening, that's a group I'm listening to for address resolution requests. When I created that link local address, I also at that time joined the all nodes multicast address. FF02::1 is as close to drunk Uncle Salty as we get in the v6 world. That's the all nodes broadcast. Then I went in and I configured a global address on this interface. You'll see that I took the last 24 bits of the global address, appended it to the solicited node multicast format, and joined that group as well. And in Cisco speak, when we do that, we also become a router for that domain. So I joined FF02::2, the all routers well-known multicast address. So one of the ponderances that comes up is, hey, in IPv6, I can use multiple IPv6 addresses on an interface. What if I had 4 prefixes, but all of them used the same last 24 bits? Is that acceptable? I mean, they're going to join the exact same multicast group, right? Because they'd all have the last 24 bits in common. Perfectly acceptable. Because there's this thing called a target address field in our neighbor discovery packets. And we'll see that here in a moment. So the setup here. Node A, Node B, they're on the same layer 2 domain. Node A wishes to initiate communication with Node B. Now, we all know from the legacy world, if I was to get Node B's IP address from DNS, I would issue an ARP, right? To get its MAC address, its layer 2 address. Of course, Node B would hear that ARP request, it would ARP reply, and I'd have the information I need to construct a frame to communicate with this device on my layer 2 domain. Well, there is no ARP in v6, right? There is no broadcast. So when I go to DNS and I get Node B's 128-bit IPv6 address, how am I going to then try to get the MAC address, the layer 2 address? And it's really simple. I'm going to take that 128-bit address, throw the first 104 bits away, grab the last 24 bits and append it to the solicited node multicast format. The frame would look like this, or sorry, the packet would look like this. So you can see it's exactly what I've done, right? And so now I'm transmitting this neighbor solicitation on my layer 2 domain to the solicited node multicast address of the target address I received in DNS, which you can see in that field there is the full 128-bit address. And this is how, if Node B actually had multiple prefixes associated, or multiple addresses associated with, how we know which one was trying to be resolved. And what I'm really asking for in this neighbor solicitation is, what's your link layer address? Node B, of course, is tuned to it and responds with a neighbor advertisement. And he gives me the information that I'm looking for, his link layer address. Now you'll notice those flags I mentioned earlier. R is set if this is a router. S is set if it's response to a solicitation. So in this case, the S would equal 1. O is set saying that you can override any information you may already have about this mapping in terms of freshness. Another little nerd note for the back of the head here. Notice that in the neighbor solicitation from A, he actually includes the source link layer address of himself, of Node A. Now, at first thought, you're thinking, okay, wait a minute, okay, wait. Here comes this neighbor solicitation, comes into me. I'm Node B. I see this thing is destined for me based on that Ethernet destination. Okay, I bring it up into the IP layer. IP, look at the next header of the v6 header. It says 58. Oh, that's ICMP. Okay, I hand it over here to ICMP. It says, oh, you're part of the neighbor discovery process or protocols. I'm going to hand you over to that process. So now I've got this information sitting at this process. I'm 1, 2, 3 layers removed from the Ethernet driver. If I was going to update the mapping for node A in my neighbor table, I'd have to reach back down to the Ethernet driver and grab that MAC address of the original transmission. Instead, how much more efficient is it for me to just pull it out of this field and make that mapping right there? So that's why we include option 1, the source link layer address, in most of the neighbor discovery packets we transmit. MLD. It's useful for multicast. Well, I'm not running multicast in my network. Actually, you are. You're running a rather complex protocol, whether you knew it or not. Multicast Listener Discovery is to IPv6 what IGMP was to the legacy protocol. Remember those days when you were imaging, gold imaging, out at remote locations and not in your data center? So basically, somebody from IT would get a brand new pallet of equipment. They'd take a piece of gear and they'd move it out to a remote location, plop it down on the desk, plug in power, plug in an Ethernet cord, turn the power switch on. Your phone would ring like crazy. This box sent a boot P request. You network guys configured IP helper address, and you forwarded that layer 3 broadcast off that domain, routed it somewhere into your infrastructure, into the data center, where the server in the data center said, oh, yeah, I know your MAC address. You're hungry for an image. Let me feed you. And so then it begins multicasting this image through your network. It gets down to the last layer 2 switch, and your switch is going like, wow. There's 100 pizzas, and I have no idea who ordered this, so I'm just going to feed everybody. So your phone's ringing, right? Now, if this device would have sent an IGMP join and snooping would have been turned on the switch could have seen the join message come up and would have said, oh, I see this guy's ordering pizza. When it arrives, I'll deliver it to this one port. So that's in a nutshell what IGMP was doing for you, and MLD does the same thing, but just for v6 instead of for the legacy protocol. Well, what could go wrong? Lots can go wrong. Lots can go wrong. First off, MLD is required to use link local as a source, as with the neighbor discovery protocols as well. MLD is required to set the hop limit of the IPv6 header to a 1. This is different from the neighbor discovery protocol. The neighbor discovery protocol requires that we set the hop limit to 255. We do this as a generalized TTL security mechanism. If we require that the reception of all neighbor discovery packets have a hop limit of 255, nobody can spoof from a remote location into that layer 2 segment, because if you go through a router, we decrement the hop limit, right? So it's generalized TTL security mechanism. So thinking says, well, gee, if we're going to do that for neighbor discovery, how come we don't do it for MLD? Well, MLD is different. We're not really worried about MLD attack from remote like we would be with neighbor discovery. But more importantly, we set it to 1 because we never want to route MLD off the layer 2 domain. Okay? Even though we never want to route neighbor discovery off the layer 2 domain, and it's not allowed, what we're really trying to protect there is that somebody figure out the hop counts and spoof information for neighbor discovery, which is vastly different from what's happening in MLD. In MLD, we're not worried about that spoofing so much because there's really no man-in-the-middle attack that can be exploited using MLD. There are DOS attacks that can be leveraged, but that's a whole different talk and a whole another hour and a half of real geekiness. The point is, we set the hop limit to 1 because we never want to route this off of the layer 2 domain for which it exists. Next, we have to put the hop-by-hop extension header on this. So if you look at the IP header, the hop limit would be set to 1, and the next header field would be set to 0, which indicates that a hop-by-hop option is to follow. And within that hop-by-hop option, we're going to set the router alert flag to a 1. This is because you might have a layer 3 device on that layer 2 segment. It's going to see a lot of multicast, especially multicast requests. It's going to see MLD reports go out looking to attach to a multicast server. And remember that the multicast server lives somewhere in your network. So the address of that multicast server is not bound to the interface, the layer 3 interface of that router on that layer 2 segment. So we use the hop-by-hop option with the router alert flag to say, hey, Mr. Router, you've got to do something with this multicast even though it's not destined for your direct interface. So Mr. Router brings it in, and what he actually has to do is if he sees an MLD report and you've got multicast running in your network, he then sends the PIM join message upstream. Now, my multicast guys, you're on board. The guys who don't know multicast, you're like, dude, could you shut up and put someone else on stage? If you ever ripped open an IGMP packet from the legacy protocol, you'd notice, first off, the protocol field in the IP header would be set to 2, which is the IP protocol IGMP, okay? And so then you'd see the IGMP message. But you got to go deeper back in that IP header. In fact, if you go deeper and look at that IP header, what you'll find is it's not the typical 20-byte IP header. It will have grown because the router alert flag is implemented in an option of the IP header. That's how the legacy protocol worked. And this is why we have to use the hop-by-hop option in v6. Well, the reason why is because there is no options field in the v6 header. Remember, it's 40 bytes fixed. So if I want to implement options, I have to move them to extension headers. Scott, you said we weren't going to talk about extension header details today. I violated the rule, see? And so the point is, I will use that extension header to alert the router that, hey, this is something I'm interested in receiving from beyond your reach. Could you please set up the connection and bring that stream down? So we already kind of covered it. 3 messages. Report, that's my desire to join a group. The done message, that's my desire to leave a group. And then the query messaging is what happens from the layer 3 interface to kind of maintain multicast groups within a layer 2 domain. We'll look at all of these in greater detail. So initially, this first version, MLD version 1, it implies a shared tree and a rendezvous point configuration. I have to go, a rendezvous point, for those who don't know, is simply an agreed upon location where the gathering will occur. Tonight, we have beer and gear next door, right? And there will be some senders, those who are handing the beer out, and there will be some receivers, those of you sitting here. The same thing's happening in our networks as it relates to the rendezvous point. So anytime I'm using MLD version 1, I'm implying a shared tree and I'm implying a rendezvous point. It's analogous in the legacy speak to IGMP version 2. If I move to MLD version 2, it's analogous to IGMP version 3, or source-specific multicasting. This says that there might be beer served in 2 locations, and I'm going to prefer to go to 1 location, the Cisco booth. Oh, sorry, shameless plug, but for fun. But that is exactly the point. You're deciding who's going to serve you that beer. Does that make sense? As opposed to going to a generalized gathering location. So this is what it looks like when a device wishes to join a multicast group. Version 1, it will send an MLD report to the multicast address of the stream it wishes to receive. Again, it's going to have that hop-by-hop option set. Router is going to see it. Router is going to forward that upstream, and the multicast will be forwarded from the router into the layer 2 domain. Leaving a group, assuming you didn't just close your laptop and head out, right? Because if we close our laptop and just walk out, did we have time to say to the group, we're leaving? No, right? No, the software's not going to do that. But if you close the application before closing the lid, it'll send an MLD done message. And so the router will see that done message, and then it will query the layer 2 domain to see if there are any other listeners. If there is another listener, that listener will respond with an identical report. Now, if there were 5 or 6 other listeners who were still on that layer 2 domain, if they see the first report, they can actually suppress their report. So it kind of cuts down on the control plane muddling. The reality is, my friends at Microsoft, I don't know, Don's in here somewhere, they actually send that out really fast. So there's a really good chance that most folks are going to suppress it. Now, if I'm using some BSD stuff, it comes out a lot later. And so we might actually have a bunch of reports before that last drink call actually comes out. And that's kind of what happens if no reports are received from that query. I send it done. Okay, I query. Wait 1 second. Query. Wait 1 second. Query. I'm going to send a last call. If I don't hear any more reports, I stop flooding that multicast into the layer 2 domain. MLD version 2 is a little different. You see, it does not make use of a rendezvous point. MLD version 2 is source-specific multicasting. So again, I can specify exactly which source I wish to receive the stream from. And because there's no rendezvous point, it does imply that there's some kind of third-party application that gives me the address, the source address of the device that's going to stream the group I'm interested in learning. And so we can use MLD version 2 to either include or exclude sources for a particular group we wish to listen to. We have ability to join channels from a variety of groups, right? So I could be streaming a multicast into the layer 2 domain from a server and then get a request to have that exact same stream brought to me from another server. So we refer to that as channels, right? It's like turning the knob on the TV. Oh, wait a minute. Sorry, Grandma. You're not in the room. It's like using our remote to change the channel. And maintenance is done with this query mechanism. Again, if the users shut the box down or do not shut the app properly, or if the app isn't properly written, we could be forwarding multicast streams into the layer 2 domain to the interested parties and never know that they've left. So every 125 seconds, or user configurable parameter, we're going to query the layer 2 domain to see which groups people still have interest in listening to. And again, think of a group as just another television channel, right? I mean, it's truly broadband in nature. Each specific multicast group is essentially another channel, the National Geographic Channel, NBC, CBS, whatever the case may be, right? And so I'm just going to query the layer 2 domain every 125 seconds, and when I get a report back, I know, okay, somebody's interested in this channel, they're interested in that channel. Hey, I didn't get a report for the National Geographic Channel. Query again, prune the National Geographic Channel. I'm just looking at specific individuals waiting for the stones to come hurling my way. Yes, you know who you are. I see you chuckling. I talked about IGMP snooping and MLD snooping, but there are some challenges with MLD snooping. First and foremost, we don't really have an RFC that standardizes how we as an industry do MLD snooping. We have some guidance, but we don't actually have a formal RFC for MLD snooping. This can cause some problems because different vendors do things different ways. What are the implications of doing MLD snooping for, let's say, Solicited Node Multicast? Be a ton of entries in your MLD table. And unless you're tying that table to do some kind of proxy response, it might actually break neighbor discovery, right? If I bring the Solicited Node Multicast into the switch and I say, oh, okay, I see that this belongs to this particular port, and I eat it, in other words, I don't forward it, how am I going to be able to resolve that guy? So right away, we've got this challenge that says, well, we probably ought to exclude Solicited Node Multicast from MLD Snooping. We reduce the tables, as Ed mentioned, and we probably allow the protocol to function. So why not take that a step further, though? Should we be doing MLD snooping for link-scoped multicast? No, we probably shouldn't. Now, I know a particular vendor who most of their products follow that logic, but not all of them. Keep your stones in your pockets. There are other implications, though. See, thinking about MLD snooping and creating entries for these things, you probably better be thinking about newer hardware. I mean, maybe even hardware that might have been developed after some of these RFCs were written. Newsflash, if you're running something like a SOUP 720 in the core of your network and you collapse core distribution and you're going to use that as the layer 3 terminus for your v6 access segments, you're going to have some problems, I'm sorry to inform you. The 720 came out well before we had these RFCs to comply with. Control plane policing might be your friend if you're stuck in older equipment environments. Let me introduce another problem that happened. Now, I call out Intel, but not necessarily to call them out, just to talk about, because by the way, the problem we're about to describe isn't just an Intel, it's an industry problem. You see, Intel made some NICs that were used by Dell, HP, Toshiba servers. They implemented MLD in a rather bizarre manner. When these devices came up, they became queriers, even though they weren't the layer 3 device on the network. Now, when that MLD report message comes out with that hop-by-hop extension header and that router alert flag, what does Mr. Router do with it? Mr. Router has no choice but to bring it into its general purpose processor. It can't fast path switch that stuff. Think about it. And by the way, that's what the RFC says to do. Exclusion being 7045 for those who are in the real know. 7045 gives the transit providers the opportunity to ignore the hop-by-hop option, but the enterprise is not relieved of that problem. Your router has to bring this thing in and deal with it. So if you have a misbehaving NIC with older equipment, guess what happens? Your phone rings. My phone rings. Well, TAC. You got a problem. Now, this was corrected. Intel's got the right drivers to fix this problem. I pointed out because you may encounter it if you just haven't updated those particular drivers and you're lighting up v6. But further, I pointed out because I believe Dave said it earlier, we're still writing. 20 years later, we're still writing. We have to move to v6. We cannot survive on the legacy protocol as we march toward 50 billion connected devices in the next 5 years. So we are still figuring some of these things out. But if you understand what's going on under the covers, it helps you solve these problems before they bite you at 3 a.m. on your weekend. Another thing bouncing around, and boy, you're going to see this stuff. The Zero Conf, okay? Apple uses Bonjour. Most of you should be aware of that. Microsoft, via Rally, has their set of protocols they use for Zero Conf for non-AD joined devices. Okay? Now, we use Bonjour for Apple TV and iTunes sharing and those kind of things. And this is what's going to bite you, is you're going to have some muckety-muck in your organization who has Apple TV in his private conference room, but he goes to deliver something in a conference room down the hall, and he can't get that Apple TV device to function because he crossed a layer 2 boundary, right? He's in a different layer 3, or across a layer 3 boundary in a different layer 2 domain. So you're going to need to know how these protocols function and what it is they're doing and why you're not going to be able to get these link scope multicasts from one layer 2 domain to the other layer 2 domain without some form of a gateway. I have just a couple minutes, so we probably aren't going to get to this particular, do any justice to it. But in a nutshell, 802.11 does not like multicast. It does not like broadcast. It treats it as second-rate citizens. Here's a quick recap of the neighbor discovery process, the amount of packets coming out just in neighbor discovery. Of course, with all this multicast going over 802.11, devices are waking up and dealing with the information, whether it's for them or not. Now, they can quickly make a decision, it's not for me, and dump it. But if they have to process it, then it causes more CPU cycle. They have to update timers, et cetera, et cetera. Now, what makes 802.11 and multicast really unfriendly is that for unicast, 802.11 frame format specifies a reliable delivery mechanism. But for multicast, that mechanism doesn't exist. So there is no reliable delivery mechanism for multicast. Further compounding it is that multicast will be relegated to the lowest configured channel. Many of you have configured away, you've turned off 1 meg, 2 meg, 5.5 meg, 6 meg channels from your Wi-Fi environment. Many of you may not even know why you did it, but one of the main reasons you did it is to support multicast. Now, think about how IPv6 uses multicast and how this problem can exasperate itself. I will move on and say one last thing for a multicast environment. You might consider setting the L bit off, especially for an environment like this where we don't do peer-to-peer networking. We don't know yet what's coming down the pipe with multicast. We do know that there are some challenges with the way v6 uses multicast and neighbor discovery. We are working on those challenges. It is absolutely deployable. You just have to be aware of where the caveats are. I thank you for your time.
Couple seconds for a couple questions. Anybody have a question?
I am just wondering if you can recommend any good books or other resources on multicast generally and v6 in particular, because I have not found much.
I agree. I've been approached on that topic, and I don't have anything yet to discuss, unfortunately. But I agree with your sentiment.
Any progress on deployment of P6 multicast in a multiverse environment?
I'm sorry.
So like, 6PE and 6VPE doing multicast?
Oh, good question. On the roadmap, but I think we have a talk coming up shortly that's going to cover a little bit of 6PE, at least from the SP side of things. I think you're asking a specific, vendor-specific question. No. Oh, okay. 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 Yes. So I know I can dump multicast into a VRF. Yes. I can encapsulate it with a wonderful protocol by the name of GRE, should you need to. But yeah, I think that's something that we have to work on. Yeah. Yeah, right. No. Wow, that's an interesting concept too. Ed, did you have something to?
Yeah, so I was curious if you wanted to comment at all, or at least give some thought around the challenges around the NIC drivers and how many multicast addresses they can actually hold versus platforms and what goes on there.
That is going to present a problem. What Ed is alluding to is that most major NIC vendors, particularly in the virtualization environment, don't have a lot of space for multicast address in their driver tables. And it could, in fact, cause some real problems if you're spinning a bunch of VMs to where this NIC doesn't have enough space to hold all the solicited node multicast groups that it may encounter. So indeed, I think Ivan gives a talk on that on the Troopers site. He has some advice and guidance there. Chip might know something more. He's always knows something deep there.
Just very short. Is there a number of hosts in that example you were giving?
Yeah, so some
10,
NICs are 128, some are 200, and some are 1,000. And I don't know.
Some are only 16.
Yeah. See, now Ed works in the data center a lot more than I do, so I'd take his word on that. All right, thank you.